Okay, today's lecture is going to be on beam bending. One of two. Today is going to be just mostly focusing on revisiting moment shear diagrams, shear moment diagrams, and then introducing just like beam stress. On Thursday, we're going to review transverse shear stress, superposition, and singularity functions for solving beam deflections. If you are currently co-enrolled in mixed solids, I'm gonna be honest, this is probably gonna go a little fast, but don't worry, like office hours are here. And also if you need any resources that helped us or helped the students last year, we are happy to share those. Just like a quick agenda, we have a mini quiz. Is everyone's homework in or like, no? Okay. Does anyone have any like thoughts they want to share like with the class, or there's also the feedback form or anything like that? Like, does this format once a week about yay long feel pretty good? Yay. Cool. Colin is going to go over some really cool data because he is smart. And then we're going to go shear moments and then talk about bending stress. Also, Katie, if now's your time you want to plug it, now's your time to plug.
Well, if anyone wants to follow my adventures.
No, not yet. Don't plug yet.
Katie just doesn't want to plug it.
Yeah. Why is it so slow? Oh my God. Oh my God.
You're struggling.
I'm gonna stop sharing for just a sec. Okay, Katie, say something.
Hello?
Nope.
No?
Nope. Nope. That's so sad. All right. Colin, do you just want to unmute? And then I'll do that.
Oh my God. Sorry. I'm talking to a blank screen. Sorry, Katie, can you plug it now?
Can you hear me now?
Oh, hello. Huh? Right. You can go for it.
Yeah, you can hear me?
Yes, okay.
Yeah. So I've been logging all of my adventures in Italy so far on Instagram on that QR code. So if you can scan it, that should go straight to the profile if you want to follow and see what I'm doing in Italy.
You suckers are taking a class. You sipping on wine, eating cheese on a balcony while making the class.
Yep.
All right. I'll go back to screen if anyone else is in the call, but Katie's here. She's awesome.
Please screen share because I'm recording.
Yeah. All right. Take it away, Professor Takeda. There we go. Okay.
So we're all here and we're kind of asking ourselves the questions like, why are you even listening to us? Like, why even kind of come to this class and actually take what we're saying as true or useful? And I think that's fair. And I wanted to know that too. Like, why should you listen to us? Where should we be getting this data for figuring out what is actually practically useful long term for actually doing a mechanical engineering career? So luckily, you don't have to listen to us. We have some access to alumni feedback and alumni data that we can use for the MEET class. I wanted to test this assumption and was fortunate enough to talk to Alessandra about getting access to this data. So for some broad context about it, originally this data was aimed to be used for kind of the MEET course and actually understanding what is kind of the changes or what is good about the ME curriculum that any alumni do use in their day-to-day, and how prepared do they feel from kind of the ME curriculum for using what they learned in their job. Maya, fortunately enough, actually worked on like cleaning up this data and analyzing it, so I was able to get more feedback from, not feedback, more context about the data. So the results from the past 5 years is that like 1 to 5 to 10 years out. I mean, there's like people from all the way like 2006 grad year that are on the survey, and there's like around 50 to 100 responses per like survey question, which I'll note in a second. There's also survey results, additionally from the past year that they were working in, and to the LEAP course that of course got shelved. And then basically Alessandra was using this data to design that course, and now we're trying to use that data to design part of this. So these are the questions that were provided at Alessandra. I'm pretty sure there's more that kind of the postgraduate like surveys are asked, but this is what we had access to. And then for each of these questions, like I was saying, there's like 50 to 100 pre-response questions, responses, and they're kind of matched to survey years and different graduate years. And then this is all anonymized, so I can't really connect any story across different questions. And I just want to acknowledge that there's probably intense amount of bias in here. I'm looking for kind of a rationale in this data that may not exist, and it's incredibly noisy, and there's just a lot of interpretations. Speaking to Alessandra, there isn't any solid conclusions you can come from it, other than there's a ton of things that alumni want. And there are tons of things that people feel that Olin did serve or did not serve them in their career. But hopefully will give us at least a little bit of an insight, just so that it's not a black box and you don't understand what we're looking at and what we're trying to figure out to kind of make this course actually useful. So broadly, like I was saying, that there's a ton of ways to interpret it. I don't know like how to kind of account for all this nuance, so I tried to make it easy by just kind of clumping up some like insights based upon some common themes, reading through all the different responses that felt most relevant to the course. So again, this filters down. There are things that this course just can't cover or talk about that maybe I really want. So kind of think about this as the course is kind of taking maybe one facet of this kind of the needs that any alumni want. So one of the large kind of broad topics I saw is that people really miss technical things. I think a lot of people feel this like acknowledgement that our mouth foundation is not very strong, our staff foundation isn't very strong, and just a need for better practical engineering. People really wanted to understand considerations regarding like different safety codes, understanding how do I even kind of do something that is safe enough? Like what is the safety factor that I need, and where does this come from? And these were kind of points that they felt were missing from the existing curriculum and really would have served them in their career. Another thing was kind of similarly more practical skills, specifically for mechanical engineering. So people time and time again were talking about the need for understanding how to make things at scale. How do we make something in the thousands to the 10,000s and so on? And how do I actually take my part and understand it when it comes to all the different manufacturing techniques? A lot of people talking about how 3D printing maybe isn't representative of the real world when it comes to graphic prototyping, and that I need to understand how to work with sheet metal instead in other aspects that aren't really covered when I'm doing something like Pi. And also it's interesting to hear like a lot of people want to see some more stuff on the business side, that they felt that wasn't really understood or covered. Or how do I even price this thing? How do I even make something that is feasible where I'm making my tens of thousands, but actually making some amount of profit to pay whoever I'm working for or pay my workers. And also, which was surprising to me, I guess, was just education on skills in the workplace. Specifically, a lot of people touched on kind of the need for looking like, how do I negotiate a salary? How do I do like workplace interactions? There seemed to be a desire for that in the classroom. I don't know if that's possible, but I think it's definitely interesting to see that is an aspect that I wasn't even considering myself. One, I guess, positive note is it was really interesting to see what people noted as Olin's edge, like what did it provide them and prep them for that they felt like put them a leg up above their coworkers. I think notably, people really touched on the idea of like design courses being strong at Olin, design thinking, systems thinking. The idea that like UOCD and scope really served them was something that I saw over and over again. Like UOCD, like I think was the thing that was pretty consistent of like a lot of people wanting to keep and maintain in the curriculum of being an essential part of how they thought about their ending curriculum. And yeah, just the ability to kind of context switch was something that people were noting. The idea that they could do kind of the grindy, like, how do I get this to work? How do I kind of figure out all the steps to get this to actual production? But also look at it from like a system perspective and think, how does this interact with other aspects of the company, ecologically, psychologically, all the different ways that this goes beyond the scope of just engineering. And that I am not just looking at this very small aspect of what this project is. And I think in a similar way, people are kind of noting the need for a change in mindset. I think we see that kind of in all the courses that we're now taking in some of the kind of like the core ME classes as we kind of transition to this new curriculum of, how do we do something that actually is useful instead of just kind of another piece of plastic that's added to kind of landfills? And how do we kind of increase or maintain that mindset in a learning environment where it's kind of hard to actually provide that impact? I thought this course of less wisdom, more thoughtfulness, were fantastic. But there are definitely a lot of people that just really wish that they had a way to kind of consider these contexts and actually think about it when it comes to when you're being told it, I guess. And this is something we're hoping to touch on in some ways. This is something that Paige has been working really, really hard on when it comes to kind of incorporating kind of safety and ethics, talking with different alumni, like industry professionals, like we've been talking about Sarah Hendren. So this is something to look at, that this is at least one thing, or one of the facets that we're hoping to approach. So I see. And then the big things are like, what is actually good, and kind of what should we do from year to year before we start making a bunch of changes. And I think some of these are kind of self-explanatory, that Olin really does give an emphasis on taking accountability for your own learning and taking charge of that. And just, we are more of a breadth school when it comes to what you're learning instead of in technical depth, and that we kind of expose you to a bunch of different topics. And this course is similar in that way, where we're kind of taking it from the idea that there is a wide variety of making tools and kind of topics that are incorporated into machine elements. We're going to give you like a quick deep dive, kind of every single class, not quick deep dive, a quick introduction to each of these topics. But it's not going to be the full breadth of it, and that it's going to give you the verbiage and kind of the things to look up later on, of how you could actually learn this and really use it in your career. But again, yeah, it's not necessarily a depth course in some ways. And these are just a couple quotes that I really enjoyed. I think the first was definitely more intense than some of the other stuff that was on the survey, but I'll just read it aloud. It's saying, mechanical engineering in the real world isn't 3D printing a plastic doohickey on a MakerBot. It's choosing manufacturing methods, choosing materials, it's doing tolerance stacks, and it's doing drawings. And that was definitely, seemed like a handful of people really felt that way, of that they really wanted to know more about when it came to the real world of engineering that we just can't have done, I guess. And then also this thing was like really, really common. I showed this presentation to Zach, and he also vehemently agreed that we have a lot of stats that's missing. So that's something also hoping to touch on. We're trying to ingrain some of the stuff that Zach has touched on in PDOs, and he did this workshop this past summer where he taught like data science to engineers. So I'm getting a lot of good feedback of how to kind of touch on the topic of statistics in this course. So also students. But yeah, this was in the past one. But we'll leave that. But largely, yeah, I just wanted to let you know that we're trying to look beyond ourselves, beyond kind of our own experiences, to try to provide a course that actually touches on what people want in their MA career, what people actually feel like they needed that Olin didn't provide. And I just didn't want to kind of keep it all on our heads so that you didn't realize kind of the rationale of why we're choosing these things, and maybe so that it's kind of a two-way trust that we are trying to do things that are effective and useful, and that this isn't us just feeling self-serving and just trying to teach a course that's kind of what we would learn. But yeah, that's it.
What the hell is this slide, Colin?
It's by break.
Okay.
Any other questions? Do you have anything, Maya? I don't know about the data.
Yeah, I guess the one thing I'll say is that a lot of the second, a lot of the things that people felt that they were prepared for weren't necessarily things that they thought was curriculum should be doing. It was just things that the question asked, what did you feel like what things in the workplace were wrong? So, especially when it comes to professional development stuff. Wanted to do that, and then the other thing was that the initial survey results. Okay, I didn't realize that you only had the alumni ones, the stuff that was specifically designed to were questions that were questions. And yeah, I just emailed institutional research and basically the last 5 years of the survey and only the responses from people who major.
Thank you, Colin. No need for Bob, right? Let's ride. Okay, so like I said, we're gonna do a brief kind of overview of beam loading and talk about beam deflection. And today is mostly gonna be revisiting moment diagrams because they are way more useful than you think. And super important. A quick peek into the future. This bottom left right here are singularity functions. Rather than doing it by hand, you have a computer like numerically do it, MATLAB or your program of choice. So we'll talk about that on Thursday, as well as on the right here. If you go to any machine or mechanical design textbook, there's usually going to be some reference table where you have known loading conditions. It's super tiny and hard to see, but you have known loading conditions where you have like either a cantilever beam or 2 points, two pin joints support a beam. Up, down, distributed load, flat distributed load. What you can do is that you can take the known solutions for those and just superimpose them on top of you have something that has a cantilever beam that's like uniformly loaded in one direction, and then there's just one random point load or moment somewhere. You can take the solutions of the known cases and then just add them together to get both the stresses and deflections. So it's a pretty useful tool. It has some extent, but I won't really touch on it. I say it's something useful just to know that you have in your back pocket if you ever need it. So it's a but basically beam bending now. Kakanoa was the name that Rob and Daniela gave us for the teaching team. We're going to show you our secret beam bending ways. Why beam bending matters is that it's really the most basic assumption. You can't have a system of like some shaft or some I-beam or something like that for a known load condition and geometry of a certain object. You can make really good assumptions on how that thing will deflect. All of this is within the realm of small deflection. What is small deflection? Ask Chris Lee. Less than 10%. I didn't know that. Thank you. But yeah. Like I said, why this does matter is that beam bending, a lot of these engineering problems can be abstracted to just simple beam bending problems. An example we'll see later in the class is that if you can treat a tooth on a gear essentially as a cantilever beam with a fixed joint right there. All gears are just spinning levers, and the actual teeth and the beam stemming from it. Not to get too far ahead of ourselves, but if you remember back to Mixed Solids, we'll get to this a little later. Like having basic beam bending, goes MC over I. That goes into a very conservative but very commonly used like stress on gear teeth called the Lewis bending equations. And the form factor is very similar. Deriving the actual like beam bending assumptions and deflections, we're not going to do that in this class. For all the things, Brian actually has a pretty good video that I do like on it, and so those are in the slides. There are a ton of other resources, including on the content review page and the Notion that has been sent to you guys a couple weeks ago. And then those of you in Mixed Solids, probably about like 4 weeks or something, you guys are going to do these derivations by hand. We're going to skip past that. We're just going to get to the like, here's the final equation, and like, here's to understand how to use it or what it's for. Oh, no, don't play that video. There we go. Okay, so when you have a beam, what we're saying is a beam of constant cross section, and then there's some supports acting on it. when you put loading on that beam, non-uniform loading, it's going to result both in shear and moment. For those not familiar, V is commonly used for shear to denote what a shear force is, and M is commonly used to denote like a moment acting upon a beam. When you have non-uniform loading, which is going to be the case, we're going to have almost all the time, the beam itself is not acting pure bending. What is pure bending? Pure bending is when you have no shear acting upon your beam and you have just a pure bend of it. So if you look at the top, like there is no sliding of things. So you can think about shear force when it's a force at like on your stress tensor. Shear force is going to cause a change in shape. Very similar for beams, you can think about it as like you have axes and grains running along it, you can see it slide. I don't have it actually with me, but there's also videos you can show online where you take like a bunch of like really strips of like ball squares, things like that, and you hold down both ends and you bend it downwards, you will see in these fibers right here, you'll see them slide together. So that's the difference between like bending versus like pure shear. However, these equations, even though it's a fraction, still very useful. Another way to drive that point home is like if you were to look at the actual like, cross section right here, there should be no change in angle when you have pure bending. Now is also a good time to talk about bending convention. We'll talk about shear convention in just a second, but in when you're talking about beam bending diagrams, a positive. Okay. When you're talking about sign convention for bending, if your beam is making is bending upwards in your up direction, whatever that might be, that is considered a positive bending moment. If it's bending downwards, like making a frowny face, that's considered a negative bending moment. It's really easy to get tripped up on this, but it just takes some practice and actually applying. It just takes some practice, yeah. I'm going to talk about like how you go from shear to moment and loading. So the slide's not super. What I should have done is I should put this part right at the top, so focus on this. But right here, the distributed load is called usually referred to as W. Like that's what your load is, and load is your like force applied or your loading distribution. It's flipped in the negative direction. So it's kind of confusing, but Q of X, when you have your actual loading condition, like the forces or whatever, you have a distributed load, you have a point moments, you have a point force acting on something. It's like conventional wisdom, like, okay, I have a downward force going right here. That's your loading curve. When you look at the actual, well, if you go back to the equations and deriving where this comes from, small radius, change in curvature, it makes more sense to make Q then acting in the upward direction or opposite of what your loading function is. And the reason we have that is because like the most classical way to solve beam bending equations and when you have deflection is the double integration method. Basically, your Q function, your loading, is the derivative of your shear, which is then the double derivative of your moment. So we have more slides to drive that home. But the biggest thing I can do to help you is to put in your mind that if I take the derivative of my moment, I get my shear. If I take the derivative of my shear, I go back to my loading function. Next class, I'll go even 2 steps beyond that, because if you start with your known deflection, take the derivative of that, you get your change in radius, take the derivative of that, you get your moment, take the derivative of that, you get your shear. That will all be driven home, so don't feel afraid. And again, you guys have all the slides here. But remembering that, like step by step, what each moment is, these are very common questions to on interviews. When you apply a force on a beam, like I said, it causes both a shearing force and a bending moment. I mentioned like to drive that home, that you better written out right here. Loading function is the double derivative of your moment and the single derivative of your shear force. If you want to put it in the actual calculus terms, it's written out right here, and this is what you'll use for doing double integration methods. We're there now. Let's talk about that moment and shear diagrams. Shear moment diagrams, I always mix it up. So you remember how, like, when we talk about internal stresses and force, if I take some body and I load it in any other function, and then I make it an imaginary line and I cut through an object, like there has to be some sort of internal shear or internal force that like holds the object inside of it. You can do the same exact thing with a beam. So if I have like a beam right here where I just have a simple support here, a simple support there. If I want to figure out what is the shear and what is the moment throughout this entire beam, there is nothing stopping me from making an imaginary cut through whatever arbitrary place where I want to do, and then asking myself, okay, with my known conditions of forces and my reaction forces here, what is both the shear and the moment acting on this imaginary line? Does anyone have any issues with that? That sounds good? No problems? Cool. Before I start going analyzing that, we need to talk about the sign convention for like my shear and my bending moments there. It gets, like I said, it can be very difficult. It took me a very long time to do this. But the positive and negative bending moment, pretty simple to remember. If it causes a negative, or if it causes a smiley face, a positive bending moment. If it causes a frowny face, that's a negative bending. Shear gets a little confusing, especially when you couple it up with how we draw both shear and moments acting upon shear and moment acting upon like the imaginary cut face. So the way I always think about it is that if I am going from left to right, which in most cases you will be, if I take my left face, and so say this is a fixed end right here, is my shear force going to be pushing it down or going to be pushing it up? If it's pushing it down, that's trying to force it into that bendy like smiley face, that is a positive shear. Even though, so like on this right here, ignore this second half right here, but this section right here, even though my arrow is pointing down, that is considered a positive shear force.
Why, could you explain why the arrows on the diagram are like the positive here and it's got the arrow specific reactions?
Sorry, what? Okay. So this diagram, like the way I like to think about it, and some people find it helpful, but like that shear still is causing a reaction moment. And so that is causing it to bend in that positive, like smiley face position. And so what I think is easier is rather than looking at the entire couple, it's like I said, like make this left part fixed, like hold it in your mind. And then is the shear force pushing it down or is it pushing it up? If it's pushing it down, that's causing a positive shear because it's going to stack like that. If it's pushing it up, like it is on the right side, that is a negative shear, and it's causing it to like bow up. I think, correct me if I'm wrong, what Avery was also saying is that if you look at the shear forces, remember how two forces equal and opposite cause a force couple cause a moment? If you look at this positive shear, that is going to cause a positive moment. And so that's why it's like associated with the positive bending. Does that help?
Yeah.
Okay.
So for these beams, are these the cross section uniform? Is that an assumption?
Yes. So for these beam bending equations, you're assuming a constant cross section.
And then the cross section has to be, I'm just thinking about an ideal meant might have more shear or something in the middle, or is that?
Yeah, so you're kind of alluding towards transverse shear, which we're going to get to discussing more in depth Thursday. But you're totally right, where if you look at a shear distribution, like especially in something like an I-beam or something like that, you will have a maximum shear right in the middle. But like that's jumping ahead, and there's some visuals I can like that will be shared on Thursday for going over that. For right now, and purely in just sheer moment land, like, we're actually gonna ignore the cross section. We're not concerned about it because it actually doesn't change the moment in shear, like, for this like simple like 1D section. When we start analyzing actual stress, that's when we get into like why your geometry matters.
This is like the average shear irrespective of cross section,
Yes,
and then there's some distribution.
yes, yeah. So then, yeah, that's a perfect way to look at it. This is an average shear. And same way where like F over A equals average, average stress across your face. There is actual distributions depending on what your geometry is, but this is still a really good approximation, especially when we're just getting started. You two want to say anything on that? Anything else to add? Okay. This is kind of like the first example problem. It's sort of worked out in the lecture slides, but if you want to do it and write it down, I think it's also very helpful to look at. Right after that question, ignore this cross section. We're not looking at it right now. When you are looking at a like beam bending problem, and you're making a moment shear moment diagram, you want to figure out, okay, where are my supports? Where are my forces? And at which sections do I want to make my imaginary cuts? Like, how many cuts do I need to make? In general, like, what you want to do is that before every moment or reaction or force acting upon a thing, you want to cut just before that, and you want to cut just after that, because there will be like a discontinuity, just jump, and whatever happens. So for this part right here, we have simple supported beam. We have a dig going here and a roller going here. We have no forces in the x direction, either x, y. So we know we don't really care about the x component of this reaction. We only care about the y. On the right side of the screen, you have a really good diagram for figuring out, okay, how many cross-section cuts do we need to make, and then how do I solve for each one? So for this first part right here, we have a 20 kilonewton force pressing down on this beam and 2.5 meters before this reacting force. So if we walk back over here, what I want to do is between that section of like 1 and 2, I want to figure out what the shear and the moment is acting upon like that section right there. As soon as once I cross over and now I'm introducing the second reaction moment, there will be change. But for each one of these, I'm like solving the free body diagram for this explicit cutout section, and then moving on to the next one, and then plotting all those forces. So for this one, it's pretty simple. We have a cut off section right here, 20 kilonewtons, and then we just have a single shear force, and we just have a single moment. The shear force obviously is just going to be the shear force here is just going to be 20 kilonewtons acting in the positive direction. So is that, like, just quick understanding, is that going to be causing a positive or a negative shear force?
Is that negative or negative?
What's up?
Is that negative?
Yes. So, yeah. So for this section right here, this is going to be a positive shear. You then might want to ask, okay, how do I solve for the moment right here? Your moment, and remember when I said your moment is your shear is the derivative of the moment. And so as x distance goes along in the next slide, you'll see you're going to have a flat value of whatever the reaction shear force is in the beam of 20 kilonewtons. And then as you go along, that your slope of the moment will be the value of your shear force.
Sorry, you said that would be a positive shear?
Did I say negative? Or did I say positive?
Yeah.
Oh, that's right. That's no, yeah, thank you. Yeah. So like it's the same thing with free body diagrams. When you're drawing them, like you always, like when you make your cutoff section, you always just want to be consistent with where you're drawing your shear and moment forces. Like if you figure out after you've done the algebra and some of forces, okay, I need to flip the direction, then flip the direction. But like when you're drawing unknown shears and moments, is that right? It's just assuming they're positive, and then you flip the sign that you need to math. Let's get that way. This is also a great time and moment. I kind of breezed over this in the past. In this section, we're just cutting on the right side and we're going to the right. And so you would draw your shear force arrow going down and your moment going this way. Also, another way to remember your positive or negative moments, right hand rule, the moment is curling around there. And so the moment is sticking out of the page, positive connection. When I make my cut on the, oops, on the way, oh, don't look. When I make my cut on the left side, so pretend like ignore this section right here. When I make my cut on the left side, and sometimes it's necessary depending on the beam bending problem that you're doing, you want to flip your arrows, you flip the direction of your cuts. I'm not going to go through each individual point right here, but you guys see how like after we have solved for the shear moment force in here, afterwards we want to have include the reaction force from the first pin joint, and then figure out what the shear moment will be on the page after that, right?
Can you ever have a positive bending moment, but then sort of a negative shear? Or is that how, like, like, can you ever have the opposite pair? Like, or can you just determine the direction of the shear just based on the direction of the bending?
I believe you can. If you have, I'd have to think more about that, right? So in the meantime, just assume no, that you should solve for both of them and do your due diligence. But I'm trying to think of a case where you would have opposite shear.
And then instead of you had forces applied on your beam, if you had moments applied on your beam, you still have.
Yeah.
It would be the same.
That's good. Okay, so afterwards, this is what your actual
Carlos.
Oh, sorry.
Just a question on the previous one. What information does like the second diagram give you as compared to the first and like the fourth as compared to?
Yeah, so that's why I don't like super love this. What I think what it does is that it kind of drives home the point that you want to sanity check yourself that like right before you have a new reaction force, right after you have a new reaction force, you should double check to see that it matches up and you should skip in your shear force values. So like in actuality, if I were solving this, like I would really like, and I was speed running through it, like I would make one cut here, and one cut here. But I think this is like essentially when you're first learning or just doing a quick review, it's not a bad idea just to sanity check right before and right after. But that's a good point. Okay, so then we go back to the actual solution for this. Again, the really only point to drive home right here is that the slope of the moment is going to equal to the value of shear force because it's derivative. Like that's really the biggest, like you're gonna take away one thing from this lecture. That's the best way to sanity check yourself when you're doing these. Another quick tip is that it's always useful to have your shear and moment diagrams like visually line up with your beam. You can get real confused if you just like draw your beam and then like the next page over or something else if they don't match up, because you want to see that jump in your shear values. Okay. Here's another example of that when we're going to actual distributed loads. So you can have point moments, you can have point forces, and you can have distributed loads, and you can have ramp loads. Yes, we do. Yeah.
So when we're doing the shear diagrams, I know that there's like a single point like shear from the reaction force, but this is one thing that I didn't really understand in my solids. Why is that like permanently semi-permanently from the graph to like upwards to positive shear for the rest of it if the shear in the beam itself from the forces that you're looking at still looks like the shear in the beams?
I think, and correct me if I'm wrong, I think you're asking like, there's this disconnect here also this, I think this answers your other question here, but we still have a negative moment in this section of the beam. Now we have a positive shear. If that makes sense, like between section 3 and 4. So like do due diligence, just make sure you look that out.
Like,
Um,
yeah, that's the 46, but why does it persist?
So why does it still persist in that moment? So if I make my cross section like right here, in between the reaction, the first pin and the second point force, like the stresses internal to that beam, there needs to be some sort of internal shear stress and some internal bending moment that prevents it from just flying off the page. Similarly to how like stress and acting upon inside of the body just prevents the thing from leaving. That force is acting upon it. Like, are you asking why there can be like such a jump? Or
One more slide. Actually, yeah, so, that one, the V3 and V4 are still going down. And I wasn't sure when that was like.
So that comes back to what I was saying, where you want to just like when you don't know the forces acting upon it, want to just like be consistent with how you're drawing your arrows in the direction of the you're facing. Like same thing like when you're doing a truss in mixed solids, like just you can immediately start, okay, I'm assuming everything is in compression, everything is compression or everything's in tension, and then if I get a negative in my calculations, I know in actuality that's going to be reversed. So like you want to be consistent in writing and drawing your direction of your arrows, and then once you solve it, if it flips, it needs to flip.
Okay, so the one that should be trusted is more sort of diagram than necessarily that.
I think what Carlos is saying is, you just assume that it's going in a direction, you draw the arrow on your diagram. If you get a negative value, you solve, you know that the force or the moment is going in the opposite direction.
Yeah.
that you assume.
These values right here, like V1, V2, like all those are not known yet. Those are not calculated.
Oh,
Those are
like
just in the three body diagram. Like we are drawing those because those are the forces we are trying to calculate.
Okay.
The placeholders. Yeah. Okay, so same thing here. Pretty simple section, not as many things. So you have to have less cuts and like a shitty just drawing here. But when you start doing seeing distributed loads, what you want to do is that you can just represent that distributed load as a single point force acting about in the center of where that load is acting. So if I look at the load diagrams, I'm trying to first calculate my reaction forces for the beam. What I can do is that if I have this distributed load of 10 newtons per meter acting across 6 meters, what I can do is that I can represent that as 60 newtons pressing down at the midpoint of this section here. That gives my reaction force for R1 and R2. Afterwards, I go back through and I make my section cuts and try to figure out where is my reaction force. Where is my shear and where is my moment. Any questions related to that explicitly?
Could you explain again why you can represent it as a point load?
Yeah, so if I have some distributed load acting across here, like there's give me a second. The moment and force acting upon here across the entire beam will equal if I, instead of like lying down on if I represent myself as a point load and I just lie down on the beam, that like force is going to increase my moment as I'm going across. If instead what I wanted to do is that I go to the center of where this distributed load is, and instead of just like I take my some weight and I go in one point, that gives me the equivalent loading and moment
For the entire beam.
for the entire beam. Yes. So like yeah, you guys have a better way to think of how to represent that?
It just feels to me like it would change the shear.
It doesn't actually. Where things get more complicated is when you have ramp functions. So like you have like the further you go along the beam, your distributed load starts increasing. for there, that's when I started going to just known solutions, and I don't really known solutions or like singularity functions, because I just don't want to spend like, okay, where's the actual center of this, and where's the like distributed. I'm sure there's calculus can do that, but I get lazy and I just do the known solutions.
Wait, I think, doesn't it change the shear? Because like, that's how you get between Q and B and M. I think the only time when you like, run a different load approximation helps for finding the reaction forces, because of. Or like, since we went between Q, B and M. Using.
Oh, I see what you
If you were
mean.
to draw, like, if you were to cut before the point load, the shear would
Yeah.
be different than if you
Yeah.
had a distributed force.
I think the point.
No, you're, no, okay, you're definitely right on that regard. No, you're absolutely right. You use that to solve for the reaction forces, and then, if I'm making a cut across there.
I
I'm
mean,
gonna get back to you on that.
I understand how it's useful for like the whole beam.
Yeah,
But if you're trying to draw a shear moment diagram.
yeah, like, there should be some slope.
Anyway, it's,
No, you're totally right about that. Oh, wait, I'm an idiot. I'm looking at the loading, not the shear. It's the shear that's changing.
Yeah.
That's why. Okay, thank you. Yes, so Avery is 100% correct. Where like, as you go walk across this, that's why you have an actual change here, and your moment will look like have more of a curve rather than just be a straight line, because your the value of your slope is changing. Okay. Okay. Once again, just driving that point home where it is the derivative of that, and actually go back one, like this is the derivative of that. Same thing, like double integration method to get to like how between shear and moment. Here, I wanted to have y'all go through the in-class example and spend about like a few minutes making your own shear moment diagram. So. Better pattern. Yeah.
So the unit for work here just be x times the.
Oh, is anyone not familiar with KIPS, by the way? Kilopounds. Yeah.
We love.
Yes, it's wonderful. Mhm. So it's just 1,000 pounds. So 20 kips is 20,000 pounds. The unit for moment would be, yeah, you can call it kip feet.
So, can I ask a
Yeah,
clarifying?
absolutely.
So the first step would be to figure out what the reaction.
Yes.
are.
Yeah. Also, full disclosure, I don't have the solution set for this, so we're just gonna throw it up on the board and see if we all jive, right? I'll make a Canvas announcement, by the way, but, if you don't have MATLAB downloaded, have that downloaded for next class.
And the solve for each slice. You just are like solving the like little mini thing like that.
Yeah, exactly. So like what you want to do is that. Cut here. Put your shear that way.
By doing this that way, do I need to specify a distance like 1 foot or?
You actually.
So I just. How do I solve it?
Well, so, well, yes, actually we do. Because the way I think about it is that like the moment is going to be increasing once I solve my shear. The moment is going to be like, increasing like X distance away from 6 feet to like 7.5 feet. Like the moment is going to be increasing, but only the like distance is a variable. So that's how I think about it. Like putting a set distance away can make that helpful and it gives you discrete points on like your moment diagram that you can do next. But once you have the moment diagram, you can like do a kind of curve.
But if I just like solve it in terms of like X, where X is.
Yes, and that's getting close to how like, when we look at superposition, how that's, superposition, how those are solved. Because in this, like, in those equations, like, you can have some, like, two hinge joints, you can have one force moment, and then like, they give you like, from like a, like, distance A away from where your beam is, which you can plug in for your known case, like, okay, A is gonna be 6 feet that way. And then that's when you solve it for the actual like, distribution. But for if it's helpful to you, I would put in an X distance away, but like as you get more experience doing it, you don't have to. Okay. Why don't we give it another like minute or two, and then there's a brave soul that wants to just like describe what they did or draw it up on the board. That'd be dope. Or do we need more time? Are we okay if we need more time? Okay.
Okay, I also got sticks and. What? I got 22 today. And not 12 is my-
Yeah.
That talks about speed.
Oh, yeah.
It's easier. But how do you do the distributed force?
Oh, is this like?
Yeah. I know, I haven't either. I saw Colin doing it. I'm like, well, that sounds like fun. Wait, it's the same results you got?
Wait, you should totally try this.
Wait, these are different. They're different? What?
So put it like.
What did I do?
Yeah.
What did I do? This much.
Like just ignore everything else and just think what is. Oh, yeah, I'm definitely.
Units are off, but it shouldn't matter.
How do you click and drag the distributed load 1.5 kips?
It's 20 and 12 and 6 and 14. These are cool. If they agree.
Is this a, like, can I see your shear? Okay, so why is it sections? So you have 20 kips? And at
20 at
14
6 feet.
You have
12.
12, yeah. Aw.
Your moment diagram is,
Yeah, your moment diagram also.
is your first thing not a pin joint?
Okay, that's what I'm getting so far. It's just-
Oh, it might be, yeah, then it's me.
This year. In this first section, right, so I drew that.
There we are. Nice.
Got it. up to course of 18. So you're
Perfect.
on that course.
You want this to go?
Yeah.
Yeah, sure. Thank you. These are cool.
What are we ultimately, like, we're trying to solve the maximum value.
Yeah, oh, so, yeah, you can figure out the maximum value. I would just do the shear moment diagram and then we'll see like what is the maximum value.
Okay, so we're just looking which.
Yeah, like this is mostly just shear moment diagram kind of overview. And then it's useful to do that because once you have that, you can actually verify your understanding. We're at FEA. Okay, I'm gonna give it 2 minutes, and if you're not finished, that's totally fine. I did have a MATLAB script for this once. It was very confusing. No, I know.
Said I'll make you into a MATLAB, buddy.
Sweet.
No.
Oh, beautiful. I thought you were gonna do an advice to simple. Like, I already got you covered. What's up? Yes, I think it's because he's right here. That'll be fixed. Yeah, and again, like. I mean, so like, this is even with, it's not like, if you can look at any numbers, this is like. So. Like I said, we get some.
Oh, okay, okay. Oh, and
I guess that's what the flexibility is.
I mean, like, I understand, I don't understand. I'm not doing so, I'm not gonna do it. Made my cuts, I'm working on it, but then I realized there's so many, I was like, I'm just gonna not. do it.
Yeah, so that's why I think it's useful.
So,
This is
close, like, I think I understand how to do the numbers, but what I'm confused about is like, so here I just was like, I'm just gonna do the easy route and just do like one list behind, just so I can actually get numbers.
Yeah. Okay,
I'm
so
like, regardless that I
so you're
like can figure out.
you haven't, yeah,
But
you guys also got 1826 for reaction.
I've got so many people got it.
Is that what? Okay, sick, so.
so like, the big one's over 18 and like a foot away.
So,
Out here.
so then what I would do is that like. You can also remember the shear for at this specific moment, that's totally right. We can also do.
Snug over.
We can also do like that moment is like the shear here, the moment is 18 times X.
Right, yeah, I have that. But then when you, so that makes sense for this first one.
Yeah.
When you get into like this
Yeah.
one,
So
because then it's like subtraction of all these others. So I don't know. About that. I think that one was supposed to be right before the next one, but
It's also super useful.
but this one should be exactly. the same,
This
right?
one
That
can be
was
exactly.
The
Your
moment.
moment will be
If assuming F,
Yeah.
like if you were writing in terms of X, that kind of encompasses that entire range.
Exactly, yeah, which is why it's, because like, so you can sanity check yourself, and I'm like, all right, I'm just gonna 9 foot here and it's 2 feet here, sorry. The points line up on this line, I just kind of want to draw, that's a good thing.
Yes. But if you just solve it in terms of area.
If you solve it for and so that variable is also useful because like you can do it so for for like when you have distributed load, X. Because it's whatever. Because like
Right, yeah.
Yeah, because like another way you can represent this is that this is 1.5 x per foot, so I can say 1.5 x times x.
Right. That makes sense, yeah. Interesting.
For those that didn't hear that, like another way to like, and this is the right way to do the new moment and shear diagram, if you're looking at the moments and the shears like not point forces. The way you can think about this is that for this section after E, I have 1.5 kicks per foot X. So what I could do is, okay, say 1.5 X, whatever my distance is going across from this section after this point. And then when I'm trying to solve for the moment caused by that, I can have 1.5 X times X, because that's more distance than the distance away from my reaction point here. And then again, those to just solve when we go to the actual shear moment diagrams, we should have the derivative of that match up. Okay, we have like two paths we could go on right now. We can just show the shear moment diagram, and then if there's any discrepancies, we can talk through it as a group. Or we can just or we can have someone work it up on the diagram here and go for the rest of class. We have about like 4 more slides that's just like intro to like MY over I for and what I is. And then next week is where the new, or not next class is where all the new stuff comes in. So this should be stuff that everyone should be not super familiar with.
My road is.
First one where you just go through the solutions. Okay, sick. Yay, what's up? All right, let's do it. I'm also a fan of this because you guys are all competent engineers and you should know what tools are at your disposal. But you should also know the downside of these tools and what it might be. So there are entire calculators for this that exist online that are super useful. However, they can also be a crutch. So like just that happened live in class where Colin and Nathan both used a online tool to figure out the shear moment diagram for this. But somebody made a mistake and like had the first point as a fixed point rather than a reaction, rather than a just pin joint. And that like swapped the positive negative shear in here. And so if you're not careful, it's like kind of similar to FEA, where if you just put like information in and have full faith in what comes out, you're going to make mistakes. But your shear moment diagram should look something approximating this. Mechanic calculus, awesome. Here, I can also send a link in the Discord for it as well, and put it on the resource page in the Notion if you guys want access to that. Yeah. Last thing to point out and reiterate is that for this like shear force here, you have 1.5x, and this slope goes down. So you see that corresponding change in slope in your moment diagram. So there we are for that. We'll post this link in there. You guys seemed like you were doing well. If you want practice, come to office hours with shear moment diagrams. I'm happy to go over it. Okay. Oh, actually, I did have one more quick example, but we are not going to go through this. You can also kind of just use intuition for this and try to figure out something. So we're not going to go through and do free body diagram. But imagine you have 2 designs for a diving board. You have like an overhung one where you just have 2 pin joints reacting there, or you have a fixed end where the entire back half of it is a fixed end. Just pure intuition wise, what do people think which design would lead to the most shear stress? On the right, okay. How many? If your vote is cantilever, raise your hand. Okay, vote is overhung. Raise your hand. Sorry, if your first vote is this, raise your hand. No shame. Everyone can close their eyes and raise your hands. It doesn't matter. Okay, if your vote is this, raise your hand. Okay, so let's actually think about this, because you have kind of 2 approximations to it. So for this first one here, because we don't have a fixed end for this 0.7 meters right here, we're going to experience some shear stresses acting in the middle. And so that's something that we're going to see. So this doesn't look too bad. We haven't done the actual forces. I just assumed like 100 kilogram force acting upon here. And this is what the shear moment diagram would look like for a case like this. Interestingly enough, for the fixed end that we have here, it actually is going to result in less force. So the reason for that is that for this fixed end right here, the moment isn't going to be applied until the very end here. And so that is actually going to lead to less stress and less forces acting across in the beam, because you're kind of effectively eliminating this first section right here. There's no forces acting across it, and the moment only acts until you're right here. So just kind of something to keep like in your mind of, and like when you're trying to build intuition for like, okay, what beam arrangement is going to have more forces inside it. Last final slides. This is, yes, sorry,
As a higher
a higher shear, yeah.
value.
Yeah, so if we go, yeah, so the actual shear, if we do the math for this, the shear acting across this section right here is gonna, well, number one, it's you're gonna have a really high negative shear here, and then you're gonna have a higher shear in this section. If you go, you can flip back and forth in the notes to see it, but like right here, we have a fixed end right here, and so we don't have any we just have a fixed moment right there. And another way to think about it is that this arrangement can't provide a moment, it has to provide a force couple. Versus this arrangement, it can provide a moment because it's a fixed end. So it makes it more simple to actually just do the free body diagram. Okay, this is speed running through kind of like what is usually like a 30-minute lecture in mixed solids. So you don't have to believe me. It's probably useful if you believe me. But when you go in and you actually start caring about the stresses and the bending stress acting across a beam, and you're considering the geometry, basically you kind of have two moments. The moment for the moment acting across the beam is going to be equivalent to your Young's modulus of whatever material it is, multiplied by I, we'll get to I in just a second, divided by your radius of curvature of radius. Which way is it? Yeah, radius of curvature. The radius of curvature, if you go through the Brian Story video, or remember back in your mixed solids notes, or you'll experience it in just a few weeks. Basically, like if you have a bending moment or a bending beam, for every point on that, you can draw a dot and see what the radius is, or like if you imagine your beam was now a full complete circle. When you do a bunch of calculus and make some approximations, the bending stress dependent on the normal forces acting in the direction of the beam, you can approximate the average stress of that as the moment at wherever point you are along your beam, multiplied by y, which y is the distance from your neutral axis, divided by I. And then I is your second moment of inertia. This is kind of like, you're gonna remember one formula for beam bending. This is the formula to remember. This is like your most basic approximation, and it'll get you close enough for whatever you're trying to do, and then you can verify your results either through FEA or something like that. What is I? I is your second moment of inertia. So if for people not in mixed solids, or people who haven't taken mixed solids right now, if I have a piece of paper and I hold it completely flat right here, it's going to droop. It's not very stiff. However, if I add a little bit more mass in the y direction against where it's trying to bend, it suddenly becomes a lot stiffer. Similarly, if you imagine a 2x4, if I put it down on a flat like this, it's gonna droop if I walk across it. But if I go vertically, it's gonna be much stiffer because there is more area above that neutral axis. The neutral axis is this y value right here. It's the dead line center of your beam. And that's where we measure like how your stress is acting upon. So that my over I, that y is the distance away from the central axis. Sometimes you'll see it as mc. C is sometimes the distance across. And I is the sum total of all the area above that central axis. Yeah, like I said, I'm speed running through this. When you have non-uniform shapes or something that you don't have a table for, you're going to use parallel axis theorem. I don't know if you guys remember that from high school physics, but basically what you want to do is that if you have some unknown shape, you're going to take the area or the initial like second order inertia that you calculate from your first end, whatever distance away that is squared, multiplied by the area of the shape. So for example, if I had some weird, like, I don't know, if I had an I-beam right here, and I have a known formula for what this second moment of inertia is for my I-beam. Let's say I now all of a sudden have this weird like hump on it on the top there. If I wanted to figure out what the total second moment of inertia for this entire thing is, what I would do is that I would take my formula, and there's charts and lookup tables for this. I can link those. If you're on Excel, it might be moving way too fast. What I could do is I could take the I, second moment of inertia for whatever this hump is. I can add it to the area of that hump, and then whatever this distance is squared. Squared is, and then add that on top of my I would then add that for the total, I would then add that to the ID. Yeah.
Or you said it was distance from the neutral axis of the ID?
Yes. Yeah. So here, let's pull that up. So if I go to, there's so many resources that you can do for this. Honestly, Wikipedia is one of my favorite ones, where if I go to if I scroll down here, yeah, area moment inertia is also common. If you want to look into the actual like calculus for where this comes from, there's a great video by Efficient Engineer about it. But basically, like what you have is if you're bending about a certain axis here and you have a known cross section, a lot of these values are already calculated. And so if you wanted to do a composite shape, that's where parallel axis theorem comes in. When you take the I of whatever your weird additional shape is. So if this imaginary hump was up here, I would take the I for that shape and then add that times the distance from the neutral axis squared multiplied by the area of whatever my weird hump is. That is most of what I have for lecture today. I know we speed ran through a lot, especially if you're co-enrolled in mixed solids. If you want to spend a little bit more time talking about this, I'm totally game for that. In the meantime, homework 2 should be posted and should be due a week from today. There should be one, it's been a few weeks, but there should be one just moment shear diagram that you have to make, one beam bending equation that you solve using superposition, and one equation you solve using singularity functions. Those last two we're going to cover in class on Thursday, but it's not super difficult and it shouldn't take a lot of time. Yeah, absolutely. Absolutely.
One other thing that's due next Monday is the first check-in for your final project, which is basically just spend like half an hour researching different ways of storing your reference resource thing. And so there's some more details on it in the on the calendar, and there's a sign up for in Canvas, so just walk through Canvas for that, and we can talk about that more. And if anybody has any questions, just reach out to us and we can chat out different ideas.
It should. Okay, it's not posted yet. I will. Can y'all not see this?